Here we have a problem that you could solve with kinematics. Let's talk about how you would solve this with kinematics. You you would say the displacement is negative 60 meters, so delta y is negative 60. It's dropped, so v initial is 0. My acceleration in the y direction is negative 9.8, and we want to know v final. So then I would use a kinematic equation and solve for v final. We're going to solve it a new way, which is using the work energy theorem. Okay. So first I want to just think about how much work does gravity do. Gravity is the only force acting on this object. Well, gravity is pulling the ball downwards and the ball moves downwards, so gravity does positive work. We've already done this actually in a previous example. I want to calculate how much work does gravity do. My formula is going to be mg delta y, and I have to choose plus or minus. I chose positive. So the work that gravity does is 2,940 joules. Since this is the only force doing work, this is the only force acting on our object, this is also the total work, or the net work, done on our object. And now I can use the work energy theorem to say that the net work is equal to delta K. And here I'm just going slowly to remind you, delta K is equal to K final minus K initial. And K final is 1/2 mv final squared. K initial is 1/2 mv initial squared. So I can just set this term here, this expression, equal to my net work. That's what I do here. Here I plugged in for the mass, and I plugged in for the fact that v initial is 0 because it's dropped. And I can solve for v final. Okay, let's do another problem. Again, it is possible to solve this with kinematics, but I want to use the work energy theorem. So press pause, try to work through this using the work energy theorem, and then press play when you want to go through it with me. So I'm going to start with a free body diagram, and let me just remind you how we would solve this with kinematics and dynamics. I would start here, I would write a net force equation, I would use that net force equation to solve for my acceleration, and then I would use my acceleration in a kinematic equation to solve for v final. Okay, we're going to do it using work energy. So there's my free body diagram. I want to calculate how much work is done on the object total. So I'm going to calculate how much work this force does, and I'm going to calculate how much work gravity does. So both forces are constant, so we only have to worry about one direction. So I can use my very simple equation to calculate the work. The d, the distance the object is moving, is going to be 50 meters. The reason I'm choosing 50 meters is I want to know how much work is done from the time it's launched to the time that it reaches 50 meters. Because the total amount of work that's done up until it reaches 50 meters is going to tell me how my kinetic energy changes from the ground up to 50 meters. So the distance the object moves, I can call it a delta y, is going to be 50 meters. So first I'll calculate the work done by the thrust force. It should be positive because the thrust force is pushing up and the object moves up, so I choose positive. It'll be equal to that thrust force times what I'm calling delta y, so that'll be 40 times 50, or 2,000 joules. The work done by gravity is equal to mg times delta y, and I'm choosing the negative. I'm choosing the negative in this case because gravity is pulling down, but the object is moving upwards, so gravity does negative work in this case. So here I've plugged in for the mass, mg, and delta y, and I get 735 joules. Sorry, negative 735 joules. So my net work is going to be the sum of those two works, or 2,000 minus 735, or 1,265 joules. This is the net amount of work being done on my object. And that total amount of work being done on my object is equal to my change in kinetic energy, which is that 1/2 mv final squared minus 1/2 mv initial squared. So here I've set my net work equal to my change in kinetic energy. I plugged in my mass, and I plugged in that it's starting from rest, so v initial equals 0, and I can solve for v final. Okay. Now I personally find this method faster than using dynamics and kinematics. But you might prefer dynamics and kinematics because that's what you practiced a lot.